Right, thank you very much. I'm going to try and set a timer for 15 minutes now, just to not annoy everybody, especially our meetup organisers. So thanks very much to Fuzzy Labs for having me. I am going to try and keep this to 15 minutes, which is no mean feat because it's actually a pretty deep subject. But there we go. Let's give it a go and see what we get to. Right. So yes, graphs. That's what I'm going to be talking about. And the kind of graphs that I don't really mean like a bar chart here. I'm talking more in the computer science sense. You know, a structure that has nodes and edges. So that's the nature of what this talk is about. A couple of fluffy slides first, just because that's what you do. You know, MLOps Anonymous. Hello, I'm Will. I'm the CEO and co-founder of ExaDev. Some other things about my background. I did a PhD in computer science at Bangor University. I previously worked for Sky as a Java dev. I worked as a data science and engineering lead for HMRC through Equal Experts for quite a few years. I had a contract stint at Google Labs as a developer on Breadboard, which is a kind of Gen AI composition agent type framework that they're building. And generally, I've worked as a bit of a FCTO / general dog's body at a bunch of different startups and scale-ups. And that is essentially the nature of what we do at ExaDev. So that we're a consultancy that builds startups and disruptive projects, and we're also kind of a venture studio. So we work with, generally speaking, I've put disruptive projects here because it's not just startups. We've also worked with enterprise like Google, Sky, HMRC, et cetera, Equal Experts. But typically when we work on those projects, it tends to be on new stuff that's pretty fast moving, pretty small teams. And we work with startups all the way up to Series A from, you know, based here in the UK, San Francisco, Australia, so all over the place, basically. But enough about that. Let's get on to some interesting stuff. So, Hypothetical, and I wanted to do this like a kind of D&D style thing because, you know, it's a nerdy event, right? So that's actually the World of Warcraft quest marker that you'll see there, for those of you who are scholars in that. So you have been hired as a data engineer, MLOps, data scientist, I don't know, some kind of data dog's body at First Platypus Bank. And your first assignment in this job is that we've got about 30 terabytes or so of customer access logs over the last 7 years that are stored across a bunch of different SQL databases, bunch of different tables. Unfortunately, we recently had a security incident at this bank. And we want to know now what in our system is most compromised. We've got a big list of compromised credentials. And we want to see what the impact of that breach was across the entirety of our system. You say, as a scholar of graph things, great, that's a graph problem. I have absolutely no idea what that means. I will show you why it's a graph problem. It is kind of a guilt by association problem. And this is what I mean when I say a graph, a structure comprised of nodes and edges. So you can imagine that if we've got customer access logs, for example, we might have a big table of events, let's say. Maybe we've seen a customer log in, and during that login, they used a certain credential to log in. And they also, during that session, perhaps, they did something with a bank account, and they did something with a different, and they logged in with a certain device. You know, they logged in from their phone or from their laptop. Well, what you've got there is, whilst you have a list of flat events, you've actually got all these different keys that you can treat as entities in a graph. And you can say, well, if we've seen both of these entities occur together, then we can draw an edge between them. And through this method, you can actually start to build up this network effect of what things we've seen interact with each other together. And so, yeah, you can imagine that this is the kind of problem, right? If you imagine the red nodes are compromised credentials, and the rest of the graph is everything else that it's connected to, well, we want to come up with an answer that's something like this. We want to be able to say, well, you know, this node here was two hops away from something that we know was compromised, and this one was 1, so it's somewhat higher risk. And those ones are infinitely far away because they've never interacted with it. So, yeah, you can see that whilst we had a kind of very bog standard SQL database, set of tables, etc., we've actually come to a graph problem in terms of what we're being asked to do. And so you can see, yeah, this is what I'm getting at. Actually, the nodes themselves are not homogeneous, so they're all kind of different entities within the system. And what that means usually, and it doesn't mean necessarily, you could store all these in a single SQL table if you wanted to, but usually the way that these things will be modeled is that you will have different tables for each of these entities, and the data associated with that entity is stored there, and so on. Yeah, and that's fine. But the question obviously will be, okay, well, it's already in a SQL database. Why can't we write some SQL to solve this? And I would say, well, you can. SQL is a Turing-complete language. You can do anything you like in SQL if you really want to. But it will probably be pretty slow. And I'm going to tell you why it will be slow. RDBMS it means Relational Database Management System, and it's my catch-all term for all kind of traditional SQL databases, which I really love, by the way. I'm a big Postgres fan. But I'm going to tell you why they kind of suck for graph problems. We've got different types of entities stored in different types of tables. If we want to get a full picture of all their interactions, we're going to have to join those tables based on their IDs. So if we have a table of interactions, we're going to have to make a bunch of joins in order to pull in the information for those other entities. And joins can be expensive at scale. What does an RDBMS actually do? Well, really, it's just a means of storing data in a file and looking it up efficiently. So an RDBMS will basically store, this is Postgres, for example. I've also oversimplified this a bit, but essentially, if you store data in a Postgres database, what happens is that we'll be writing this data to disk, and it will be in a bunch of different page files. Postgres uses 8 kilobyte page files by default. And when we want to look up a particular key, so let's say we want to look up account number 87654321. Well, we have something called an index, and we will look through that index, and the index will tell us what page file we need to look in order to retrieve that data. And the oversimplification is that this isn't really just a lookup table like this. It's actually a kind of tree index, and there's a lot more to it. But ultimately, that's the core concept. So why does that kind of suck for graph problems? Well, it's because if we want to explore relationships really, really deeply, each time we want to jump and join two entities, we're going to be using a join to do that. And each join is going to use quite a lot of CPU instructions. And I'm not saying it's going to be incredibly onerous, but especially once you get into really, really big graphs with hundreds of millions of nodes and billions of edges, this is just going to be an overwhelming amount of work. And there are much more efficient ways to do this. If there's one thing that you take away from this talk, it is basically that hopefully you will be slightly better equipped to spot where you might have a graph problem. And that would be if you are writing queries in a SQL database where you are doing left join, left join, left join, left join, left join, left join to bring in lots of different relationships, you should be thinking, hang on, there might actually be a graph problem here because I'm joining a lot of different things together. Especially if it's at scale. If it's small scale, who cares? Like using RDBMS, it's going to be fantastic, right? But this is the advantage of graph native storage. If you don't store this data in an RDBMS, but you store it in some kind of graph native storage, it will be much faster to explore. Why? Because the defining characteristic of a graph data store is something called index-free adjacency. Adjacency meaning when you have two nodes or vertices next to each other, then we have an index-free way of going to the next piece of information. It's a big linked list. If you've ever done CS, that's all a kind of native graph data store is. It's a massive multiply linked list. We have pointers to where the next piece of data is that we can follow, ideally, with a single CPU instruction. So our traversal of these graphs is constant time if we have them in this kind of native format. Okay, cool. Didn't really understand all that, but it sounds like what you're suggesting is something pretty crazy, right? We're suggesting, and let's say we've got hundreds of thousands of compromised credentials, and we've got a graph of hundreds of millions of nodes, or in this case, billions of nodes, let's say, tens of billions of edges. You're suggesting to do a breadth-first search from hundreds of thousands of different starting points simultaneously across a graph of this size. Like, it sounds completely absurd. How can you do this in a reasonable length of time? Well, actually, there's two ways that you can do this in a reasonable length of time. And this is where, you know, the focus changes to big data for graphs. There's special ways that we make this really efficient. One method is called bulk synchronous parallel. And one example of this is there's a famous algorithm that Google came up with in 2010 that they used to underpin a lot of their graph algorithms called Prego. But basically, it is a way of reformulating the problem that we want to solve into a way that only requires the state of one vertex or node at a time to be considered. And that means that it can be massively, massively parallelizable. I'm going to work through this example just to sort of show you what I mean. So we want to do a breadth-first search. So what we're going to do is at step 0, at the first step in our algorithm, we're going to mark this first node as being guilty, because we're doing guilt by association. Right? So we're going to say, all right, v sub 0, let's say, you know, in this case, the sub number here is the step of the algorithm we're on. So at step 0, we initialize this first node to have a state of 0, which is its distance from something guilty. It has a distance from something guilty of 0 because it is itself guilty. And essentially, we use a message passing algorithm. So every time, the first step of the algorithm, we will pass a message just to the guilty nodes, and we will say, all right, the content of our message is 0, your vertex state is 0, and now the new vertex state is going to be the minimum of the current state and the message, which stays as 0. And then what we're going to do is we're going to pass, that's a synchronized step across the whole graph. All of those operations happen in parallel. Those nodes that receive messages have been updated. At that point, we're going to pass messages to their neighboring nodes, and we're going to send a message of the vertex state plus 1. So we're going to send, this node is going to send a message to its neighbor with 1. The other nodes we've initialized to be infinity, because we don't know how far away they are from anything guilty so far. And then at the next step, this node performs the same calculation. It says, right, my state becomes equal to the minimum of my current state and the message I received. In this case, 1 is less than infinity, I hope. So we set the state to 1. And then the next time, we pass another message, and we pass state plus 1, which is 2. And then this node does the same calculation. What's the minimum of infinity and 2? And you can see how this information propagates across the graph, where you only have to do these very parallelizable calculations at one given time. So it's very, very parallelizable. And those of you who've got a computer graphics interest will notice that this is exactly how a vertex shader works in your graphics card. If you've ever written a HLSL program or something like this, that's exactly how it works. It's the same conceptual model. Vertex-oriented computing, managing to do all of these tasks in bulk, in parallel, but in synchronous steps. That's one way. There is also another way, a more mathsy way. As Matt did ask me to put some kind of maths in the slides, so here it is. You can also formulate any kind of graph problem in terms of linear algebra. How do you do that? Well, you can represent a graph, any graph, as an adjacency matrix, which basically is one of these. It's a matrix of zeros and ones, and we say, so the way to interpret this matrix is to say, for example, if you imagine the rows and the columns having numbers 0 to 4, you could say row 0, column 1. If there's a 1, there's an edge between those two nodes. So nodes will be in the columns, and the presence of a 1 or a 0 indicates whether there's an edge there. And the fact that you can represent the graph as a matrix means that you can do clever linear algebraic matrix operations to perform exactly the same task through kind of repeated multiplication. Now, I'm not going to read through all this because I'm quite short on time, and I don't think that's going to be interesting to anyone, but it's interesting to point out that you can do this, and this is probably, if you have the opportunity to do this way, going to be the most efficient to run on a GPU, for example, because GPUs will eat these kind of matrix calculations all day long, really, really fast. However, you can't fit you can't always generate up-to-date adjacency matrix very easily for these graphs. That's kind of the downside. So, yeah, what can we do? What does this unlock for us in machine learning terms? Some interesting stuff, actually. So there's a sense that the data that we have here, for example, customer interaction data, especially in security terms, often the structure surrounding the data is more interesting than the attributes of the data itself. And the example I would give is like, you might look at an individual device, for example. Let's say you've got some model that predicts whether a device is doing something dodgy or not. And you look at the attributes of the device and you say, well, you know, it's got a sensible looking age, it's got a cookie, you know, it's had normal looking sessions. There's nothing particularly unusual about it. And you would see, if you had a human looking at it, you would see that the unusual thing was that it connected to lots of different accounts, for example, or it's been used from lots of different countries, or it was used from, you know, used in tandem with another device that was suspicious in terms of its activity. And often such models will be written in an attribute-based way, because that's the way that the data is structured in SQL tables, right? You naturally roll up the device table and you do count and you produce some features and blah, 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 and you produce a model and it looks like it's doing a good job. But actually the interesting feature is in the structure around it, its interactions. And so if you have a graph representation, you actually get all of this context for free, because you can just cheaply pull a neighborhood from any given entity. And the cool thing is, if you can pull a neighborhood, you can turn it into features for a model, such as using an algorithm like graph2vec, which will basically produce some vector representation of an arbitrary graph structure that you give it. So yeah, this is a way that you can produce much better features for your ML if you need that kind of surrounding context, which is often the case in kind of security applications. And I've gone just about a minute over, I think, so I'm going to call it there.
All right, you keep hold of the mic, I'll shout, because we've only got one working mic, so we'll do some questions. If you could just repeat the questions back so everyone can hear them as well.
I'll do my best.
All right, so I really enjoyed that, and I think that distinction between when you do a graph database and when you do an RDBMS is really interesting. And I always think, yes, it's if you're doing those long chains of left joins is one signal, but also I guess you can think of a graph as like you've already done the joins. Every possible join you could need, yes. You've already done it. I think that the downside, I suppose, is where actually if you wanted your joins to involve a very large number of rows, it's not so efficient, right, because of the traversal.
Yes.
Is that about right?
Yeah, that's right. But also I would say, like, you know, they're two different storage formats for two different applications, right? And both are right. And it's kind of like the other advantage of graphs is that it's cheap to explore arbitrarily small neighborhoods. So it's like, oh, I've got this one key and I want to get things around it. Well, I can do that really, really cheaply with a graph, but with an RDBMS, I have to worry about joins and rows and row counts and pulling out and limits and stuff. And, you know, it lends itself less naturally to that kind of problem.
Yep, that makes sense. Yeah. Any questions then? Any further reading you can recommend?
Well, where can somebody find more? So I wouldn't get deep into like academic texts or things. My favourite resource was probably I think there's a Python package called NetworkX, which implements almost all of the graph algorithms you can imagine, and their documentation is outstandingly good. And it gives you kind of a platform to actually play with a lot of these algorithms on smaller graphs. So my best option for learning about this stuff would be, you know, just go and have a tinker in a little Python project with NetworkX, and and then read the docs, because each algorithm is pretty well documented, and you can go and read the source code, and it's actually pretty legible and simple.
And plus, there were a couple of papers that were in your talk as well that you suggested, right?
I did list a couple of papers, but I kind of listed them more because they were things that I mentioned. So one of them was Prego, which is that's a 2010 paper from Google, which kind of introduces this bulk synchronous parallel approach. I They didn't invent it, but they kind of, in typical fashion, that seems to have all the citations because it came out of Google. But I also mentioned on the previous slide Graph2Vec, which is a cool little paper. Not actually something I've used, but I was like super enthused about the idea of just kind of, like Word2Vec, but for graph structure. It's like, here's some graph structure, give me a nice vector that I can use for my ML model. And that was a 2017 paper called Graph2Vec, which is quite interesting and probably worth a read if you're so minded.
Fantastic. One over here?
Yeah, just so for your use case, you've been given these SQL tables, right? You haven't got the graph database. So within this approach, is it, as a long-standing solution to this problem, it would be worth converting those into having it also a graph database, or is it more efficient to convert those SQL tables to a graph database as a wider? Because I imagine it would be the first one.
Well, yeah, it's about like whether it's worth putting this into that storage format. And actually, it's not that hard to move it into that format. All you need is to transform the entire thing into essentially a list of nodes and a list of edges. So it's actually not as difficult as you think. And at that point, you can, the important thing is that once you're processing things in memory, that you have everything in a graph native format. And you can load it into loads of different graph native formats from a list of nodes and edges. Like the one I have most experience with is like using like GraphX on Spark, for example. So you've got this kind of that's like a Spark native graph representation. So, but you could use anything. You could use Neo4j. You could use any of these other graph platforms. Yeah, it's just about if you identify that you've got a problem that you're probably not going to have enough time to do the compute, or it's going to be absurd amount of compute if you don't do it in a graph way, then it's worth. It's not actually that big a job to dump this amount of data, as long as it's well structured, into a graph format. Just nodes and edges. That's all it is.
Go ahead, Scott.
Yeah, if I've understood it correctly, would inserts become more costly compared to a relational database?
Yeah, so this is an interesting point, which is so it's not just that they become more costly. In fact, inserts are very cheap on the face of it. What is expensive is that you're processing. So if you've done a huge graph algorithm over a graph with billions of nodes and billions of edges, right? And you've produced some result, and you've labeled every node with a distance to its nearest risky thing, for example. Well, if a bunch of data has come in that time, you don't know what it could have been connected to. So that entire huge calculation that you did has immediately become out of date. So that is kind of the downside with inserts. Any single node can have with edges can have an enormous impact on the result of your computation.
And depending on what features, like if you've done Graph2Vec to extract features, I suppose depending on what features you've extracted, that may also have to change.
Yes.
Right?
This is like another sort of check against doing the adjacency matrix thing, and this is why actually you'll find most of the big data graph approaches will use this kind of bulk synchronous parallel approach, because you can explore subgraphs much more easily, much more cheaply. You don't have to compute the full adjacency matrix every time when you might have data streaming into the graph all the time.
Fantastic. Should we move on to the next speaker?